Okay. Everybody online hear me all right? Okay. So engineering with nature is a couple things. It's a way of thinking about how we do our engineering. It's also a program that the Corps of Engineers has for thinking about how we do our engineering. There's money that goes along with it. And that program is actually what has funded a lot of us being here today. So that's really cool. But really beyond just the programmatic funding, engineering with nature is really a philosophy of how we design and how we do what we do. When we're engineering. So this guy right here, if Chuck is the godfather of GSSHA, this guy, Todd Bridges, is the godfather of engineering with nature. Cool. So initially, this quote right here really captures what is engineering with nature. If you're trying to say what is engineering with nature, just beside the little catchphrase, right? And you can really actually pick this apart and work on different aspects of this and put it together. It's a good quote. Engineering with nature is the intentional alignment of natural and engineering processes to efficiently and sustainably deliver economic, environmental, and social benefits through collaboration. So it's really all about putting together natural processes and engineered processes, right? We're going to spend the time and effort and brain power to put the two together. This is the Engineering of Nature website. You can go in. It's been active for several years now. You can find lots of good news stories about projects that have been done. Mostly, they focused on the coastal realm. Yeah. Dredging. There's really nothing to do with watershed management. We're breaking ground today with doing this class right now. We're going to put all the recordings up there, put all the presentations up there. We're really breaking ground with showing how we can do engineering of nature in a watershed management context. The good news is we've been doing this as hydrologists for decades, so this is nothing really super new for us. But framing and putting it together is kind of new to us. And I would say how we do it with GSSHA and WMS. We'll walk through that. So, watershed engineering with nature. So again, going back to engineering with nature, it's the intentional alignment of natural processes and engineered processes. Right? So you've got to really think about process level descriptions. Right? We've done this a whole lot throughout the course. We're thinking through runoff as it goes over the lands. How do we go through wetlands? How do we do sediment runoff? How do we infiltrate? Right? What are the different processes and how do they break down and work together? The reason why we put sediment transport into this, right? We just kind of threw what would normally be a month-long college graduate level course of sediment transport. We threw that at you in like under an hour, right? So don't feel bad if really quickly over your head. But understanding geomorphology and how the watershed, the land, the topography responds to what we do as hydrologists is important, right? So I wanted to explore y'all to that. Obviously, the hydrologic processes, right? Those change, and that's what we deal with as hydrologists. On a day-to-day basis. That's our bread and butter. Managing and understanding those processes, understanding how they connect and where they disconnect, and how do we put those together. What we generally are not so good at as hydrologists and engineers is the ecological systems, right? We tend to leave those for somebody else, but those are just as important because those are processes that play a role in geomorphology, landscape structure, and they feed back into hydrologic processes. So the more we take the time and effort to get spun up on ecologic systems and ecologic processes that influence our processes, the better we are as engineers. This is the one slide version of a, again, graduate level semester level course. This is, I got two slides on one slide here. When you're looking at a watershed, and I've got a few slides on this, but really what I want to get to is the holistic concept of how the different parts and pieces of the watershed fit together. Okay? So locally, it's kind of easy to go, okay, we've got some little patch of land, feeds it to a stream here, we set up a little hydrologic model, good to go, done, right? When you're looking at something like this is much more continental scale, right? You've got mountains that sort of go all the way down the coast, right? In our watersheds, we've got a miniature version of this, generally wherever you go, okay? We've got up here are your first order streams, your headwater streams, right? They're going to be feeding and sort of pulling in a lot of sediments off the lands. There's going to be sort of this transfer zone where the water starts to aggregate, the erosive power starts to aggregate, whatever sediment got pulled off starts to aggregate, and this is sort of the transfer zone here, and then down here is the depositional zone. So when you're gonna, in the case of a local riverine system, before it goes into another larger river, it could be a depositional zone, or maybe it just keeps on going. Right? But what you should notice here, the slope plays a huge role here. How steep everything is really depends on whether are you eroding, transferring, or depositing. Right? So if you're flatter, you're much more likely to deposit. Right? So these zones can very much happen in any watershed, small or big. So you want to kind of keep this in the back of your mind, like how is sediment moving, how is erosion happening, where is the water being generated from? Where is it moving through? Where is it grabbing the sediments? Where is it interacting with vegetation? And how does those interactions happen? Because those are the processes that we're going to try and engineer. In rivers, I'm going to give it 2 for 1 here. This one's like everything shoved together. A lot happens inside rivers, right? Like I mentioned when I talked about channel flow, like you've got, beautiful flow that goes through the river. So that's what comes the meandering back and forth. You've got the meandering, the them cutting through everything. That's going to cause all these different terraces. And these sort of back basins and natural levees. You'll find different grain sizes, so preferentially deposits on different parts of streams. All right, so these levees are going to be larger grain sizes, maybe cobbles even, from when the river was higher and it was moving a lot more stuff. The cobbles sort of settled out on the sides a lot faster. When the river dropped back down, you've got a lot more of the fines and smaller stuff moving down the bottom. You'll see a lot of sand, gravels, a lot of these bars right here. So from trying to put those 3 different processes together, right? We've got different stages of the hydrologic cycle, even within the river system, sort of moving preferential sediment, different locations within one little small section of a river. Right? Tack onto this, the ecology, right? So, like gravel beds right here, if you're in the Northwest, that's where your salmon spawn. If you don't have those gravel beds because you've altered the ecology and the sediment movement in your system, you've just killed hundreds of thousands of salmon out of your rivers. So understanding those different processes, how the biologic, ecologic processes fit together with the sediment and the hydrologic processes is important for understanding these systems and how we engineer them with nature. So scale and scaling in hydrology. So now I spend a lot of time talking about this in advance. We, in hydrology, we have a challenge where we cross multiple scales from micro topography to giant river systems, right? Mountain ranges to small hills, everything in between. So we move water, we move sediment across multiple scales. And that's both a challenge and an opportunity, right? So for a model like GSSHA that lets us get at those different scales, it's a good thing. We can start to dig into what are the different processes that happen at the different scales. How do they work? How do they move water, move sediment? So if you think sort of all the stuff in between the rivers, right? That's land cover. That's where we're having the overland flow runoff, right? We're getting that real thin sheet flow on a really good day, right? We got some microtopography, we've got some sort of, little rills, little pockets of water moving around, right? Land cover is going to be the biggest influence that we can do there. You're not going to throw in, a dam and influence a whole lot of space upstream because it's all very thin, just the topsoil layer that you're working through. Next up, you're looking at your small order streams. We've got a lot of them. Less than all the space in between, right? So that's good news. There's fewer of them than the space in between all the streams. But they still don't impact quite as much, right? They're going to impact some stuff. They're going to have an upland area, but they're not going to be as impactful as the streams that are more further down. So we scale both in our ability to impact and touch things, but also in the cost of doing things, right? So we're trying to do land cover change, land change. We're going to be having to do, blanket large swaths of the watershed with different kinds of plants or different tooling practices for the farmers or cropping practices. Okay. We're trying to do sort of more targeted. We've got, $30 million. We can do one big project, but we're going to look more downstream in the watershed. And this really gets to the fractal nature of stream networks. So fractals are really cool. They're sort of this mathematical way of thinking through things. So this is one such kind of fractal that's a tree structure. Okay? So really you just take one line here and then split it two, split it two, split it two, split it two, and sort of keep going. That's all it is. So here is the GSSHA watershed that I showed you way back when yesterday. It's like forever ago. Let's start down here with one and splits into two, and that one splits into two, right? That's kind of how this goes. So this is the paper talks about the fractal nature of stream networks. I think this is a helpful way of sort of thinking through different scales and sort of how you have to think about how they transition across the watershed domain. So first we have sort of this very ring on the outside. So we've got, notice I've got sort of the space out here. That's all the stuff that's not part of the stream network, right? And then we've got all the little bitty, tiny first order, maybe some little second order, little bitty streams. Right? That's sort of on the very outside fringes of our fractal tree here. Inside that, sort of stepping closer down, closer to the outlet here, where now we've got more stuff coming together. Right? We're not little bitty stuff now, but we're not the big stuff either. This is sort of the in the middle range, right? So there's still a few little bitty things, but much more. We've got second and third order streams kind of coming together, starting to make a bigger difference in our watershed, right? We've aggregated more upstream area. Right? If you're on the EM delineation, then you're down on those, 500 levels instead of the 30 levels. Like, so when you think about these, so this sort of everyone here, but you can see by the time you get down here, you're influencing a lot, right? All the water is aggregating together. It's all coming together. You're able to have sort of big impacts on the water side of things. Now, if you want to do interventions or you want to change things, this outer ring, you're going to end up doing a lot of little things. Because you need to have sort of spread thin. You've got a lot of land surface you've got to cover, you've got a lot of little freshwater streams you've got to cover. So whatever processes you're looking at, whatever engineering you're looking at doing, you have to think small scale, but a lot of it. Across the watershed. Now, as you get sort of closer to the middle here, we're going to scale up in size of our interventions. The projects themselves will be bigger, cover more acreage, more land, right? So we're going to have fewer of them, right? So we're sort of transitioning from this, a lot more little, fewer bigger ones, and then we can target like one or two, bigger ones down lower in the watershed. Okay. So when you look at this sort of model of how interventions and sort of our practices as engineers need to be applied across different parts of the watershed. So think back to what I showed you guys about the Kishwaukee watershed, right? So here was this one little tiny wetlands, right? That I was, day one, just trying to show up empty-handed and show, hey, we could move this little tiny wetland around. If I move the wetland down here, moving down this way, my little fractal tree, right? If I'm moving my wetland up here, moving up here, fractal tree. So that's kind of how those.
A question.
Yes.
So would you say if we're higher in the network for more nature, and as we go lower for more engineering?
No, just the scale has to change. How big the projects are.
Yes, big projects to me mean engineering.
That's the can't very much. They are, let's listen.
Yeah, I think it's a really great concept. The fractal itself, is the self-similarity. For example, you do the whole tree, right? You plug out a small branch from the tree. That is similar. So it's a replication of big into small. I think it's a good concept that kind of fractional dimension that plays around equally for all that scales, the work that probably translates that we apply for nature, the small scale, equally for the bigger scale, right? But how you translate, there should be some like dimension that is constant overall, but the application could be different. Yeah, but give the result similar. That's your visual effect is similar, just like the output is similar.
Yes.
Yeah, great concept.
And sort of to get back to what you're thinking, Chuck, as we're thinking through the different watershed processes, the different watershed processes like retention depth, right? That is something that's way out here on the trenches, right? So we can target retention depth changes, with little tiny things that are planned over. We're not going to be worried about retention depth in the middle. We're going to have to do something that actually targets a much bigger process. Does that make sense? So here's the Kishwaukee watershed. So if you notice, the watershed is different sizes down here, right? We have some of these have different. This one has a lot of urban areas. This one, more urban areas over here, small watershed, there's wetland here. More medium-sized wetland here, moderate urbanization. Here's a very large, and it's targeting way downstream. So this one that was a large, very far downstream was the one that had the most impact. Well, because it actually aligned big target area down in the watershed, down low in the sort of fractal domain of the watershed. Whereas the others didn't have a lot of impact because they were sort of much more diffuse in targeting those upper leaf little branches with all the little tiny changes that were much more minor. So the Provo River watershed, this is kind of one of those sort of bigger ones that is some engineering and nature sort of put together, right? So the Provo River watershed, Provo River restoration. Provo River used to look like this. It was just a straight. Back in the 50s, the engineers loved nice straight, very straight everything. They just went, that's pushing must.
Fix it. Inefficient.
So you can see right here, this was the old street bed right here. So they spent a lot of time, a lot of effort to buy all the acreage here, to dig out and make this thing continuous, to put in all of these little side channels, to actually make this, large scale project to restore Patrick. So this was really looking at how can they restore habitat for trout? How can they make this back from a barren, minimalist, very simple ecosystem and turn it into a complex ecosystem that supports a wide variety of fish, plants, and people wanting to come enjoy it. So there's wetlands now. There's a lot of good. All these little things like ripples here, ripples here, ripples down here. That's where all the trout like to spawn. So big projects. Where is it at? It's actually between two really big reservoirs. So here. This is all mountain, so right about here is where that project. So it's further down, right? So it's more at the right scale for capturing things, and it kind of helps that they've got a reservoir right here that has like a mandated release, so that they can have the environmental flows. So on the other spectrum of things is the city of Detroit, which this really shocked me. I'll be honest, I was not expecting this out of the city of Detroit. But the Detroit district asked me to help with the project, and then so I started looking into this, and I came across this, and I was like blown away. So all of these, like 269 projects. This is all it. They've got a good, nice mapping interface. You can zoom in and see all the projects. Right? But these are all little tiny projects. These are targeted local projects. These aren't many, hundreds of acre scale projects. These are, a third of this acre at best, right? Scale projects. But they have a lot of them. And this is targeting all the little tiny branches on that scale. So they have a lot of these bioretention soils where, just next to the edge of a parking lot or along a road. Spend money to build a little retention this year, put some grass in it, trees in it, some plants, make it look nice, make it be able to retain water, provide some greenery, cool the area, and it's all pretty good. These right here are actually abandoned houses that were one per kid. So the city bought the lands, took out the old abandoned house, and put in these bioretention ponds. So there's actually other plants right here. You can't really see the diagram here, but they actually dug out and made like a bioretention space. So there's a space underneath for water to actually come and sit there and eventually sort of infiltrate into the earth. So the little neighborhood here, now the runoff from the storm flows into this water retention pond instead of off into the road route. Right. So they have hundreds of these, right? That's these little disconnects, these little tiny projects. They sort of capture the idea of we need a lot of these little targeted things. The other thing that they did was permeable pavement. So they actually resurfaced some of the roads. And these edges right here, you can see here's the rain. Here's the rain just soaks right through the pavement, right? They got the storage area underneath where the rain can go into it. So I didn't even know we could do this with asphalt, but sure.
I know you can do that on the road. I know all about the parking. I've never seen that.
Yeah, no, this is really cool. And this is their design, right? So they're targeting street corners around businesses, right? Let's put in some trees. I don't know how to see the words here. Pervious pavers, little brown areas, right? You've got vegetated swale with salt tolerant ground cover. These little light green areas. You know, stormwater treatment with subsurface storage. So all of these right here, the pervious pavers, all these have subsurface storage. So they can capture the rainwater, let it infiltrate, and not feed it to the big giant stormwater system. So, City of Detroit, like I said, blown away. So really impressive how they really tackle this. One of the things you have to sort of think through is where in the watersheds do possibly transition from one process to another process. So those, if you sort of think in a, complexity of process, what's moving the water? How is the water moving? What is the major conveyance systems that's moving the water, right? So at the very beginning, we've got overland flow, right? But at the very beginning, we don't even have overland flow. Water is just sitting there in the retention depth, right? The little microtopography. And then we finally get enough of it, and we switch from it's sitting there in the microtopography to now we have overland flow. Eventually, we get enough overland flow that we switch from sheet flow to now we have a stream. In the case of a lot of cities, they'll switch from we've got a stream to now we've got a storm drainage. Right? And if you get enough, well, now we're going to go back the other way, right? So maybe we've got our stream, but our stream is overflowing, and now it's back onto the overflow. Right? So we switch processes that are moving the water in time and in space. Well, this was an interesting. Another process that's changing that we sort of don't recognize. This was from nature. This was how much, where has land use changed over the last 60 years? You look here, here's the US, right? Large part from the US, basically 17% of the entire land surface of the earth has a different land use today than it did. So in our watersheds, even how the land is being used is changing. But we don't know how to see that, right? Houses going up, farmers not farming, whatever. So here it is. I've got a couple slides on a study that was done. It wasn't done by me. Justin Zill and Fred Ogden, looking at storm drainage networks. So this was in Baltimore. The question was how well the storm drainage networks handle big flood events like a hurricane. So urbanization, as we all know, it was lots of more impervious area used to work on. But everybody, cities like to put in subsurface drainage. City of Detroit, They no longer have streams. Everything is subsurface drainage. They don't have streams. At the same time, the geomorphological changes in the watershed, right? All the urbanization changes the topography, the connectivity of different parts of the land, how it works. So none of the natural drainage is being charged. And thus, because everything's natural restricted and less pervious, right, you got more runoff time. So this was looking at the drainage system, looking at sort of testing it. Here is existing channel and drainage network. Here is a channel network. So the drainage density, so you take the area of linear length of all of the stream network pipes and all that, divided by the area of watershed, right? So we get it the same. So comparing just streams to pipes. Same amount of stuff. What's the difference? They even went through the process to show where in the watershed, how far from the outlet is the stream versus the pipes. It's the same. Pipes kind of are in the same general locations as where the stream. But how much water can actually move at those locations? You move so much less than the pipes. So your conveyance, how much water you can actually move, even though it seems like you have all the same amount of stuff, is completely different. So open channel network conveyance way bigger than the social bridge. So when you send a big storm, the big storms easily overwhelm the pipe network, and flow changes back to whatever else is there. In this case, nothing, because it's all paved over. So now it becomes flooding in your neighborhood. So this is just one of those examples where we have sort of a concrete study of how big of a flood can a particular subsystem of your watershed have. But thinking through that, sort of concept applies to all the different subsystems. They can only handle so much, right? So if you have wetlands in your watershed, well, they can only handle so much, right? They can't handle like the storm stuff. If you've got infiltration basins, they're not going to handle so much. Your retention depths, all going to handle so much, right? All these things sort of have their natural scale at which they operate. There are a few different groups out there who are helping to sort of frame and focus this that I wanted to sort of bring into the picture here. So this is actually from the Nature Conservancy. So the Nature journal article is nature.com. The Nature Conservancy is you gotta be careful. The Nature Conservancy is a group of citizens who are concerned about rewilding spaces.
It's a nonprofit. It's a nonprofit.
Nonprofit.
I won't see.
They're actually really smart, good people to work with. Like these are like good. They're good. So they've come up with just recently this leading at the edge. So this is how can farmers utilize these same concepts we've talked about to better manage their farm. Right? So they're encouraging farmers to put in riparian buffers along the edges of the stream. Right?
What is that?
So that's where you've got some grass or trees between your crops and the stream, right? So it's not just like, let's farm every last inch of dirt.
And you're not letting the livestock graze it.
Graze, right? So you're excluding
Excluding.
livestock.
Yeah.
So drainage, water management. So if you've got drains, you're not sort of literally dumping that out, but you're managing your drainage water. pitches. Instead of having straight, Minnesota, Watershed, totally fine. Will be straight the pitches, right? So they're encouraging these two stage pitches, so that on the shoulders, you've got plants. Absorption a little harder.
What is the drainage water management? What are you going to do? Is that a thing where they store the runoff? Oh, and they reuse the runoff?
Reuse it or slow it down.
Doesn't it, it kind of acts like a weir also, doesn't it? Like it kind of, you'll have it set at like a certain level, so it'll kind of slow it from,
Yeah, it's called an aggregate.
yeah, yeah,
Yeah,
that's how,
and it controls the water depth in the field because it essentially either backs up or opens the tile drain.
Yeah,
I'm from Minnesota.
yeah, it's a control on tile drawing.
All I know is that if they did that in Florida, we wouldn't have much, like, we could reuse the fertilizer that's in the runoff. And you don't have to
Recycle that.
Yeah.
Prairie strips, so having space here where. You have vegetation that can impact nitrogen. You can cycle water just for a while. Well. Then they have wetlands, so that you're not just, like water dumps straight off into a river, but it fast. With the nature reserve people, they're pushing and trying to help these ideas take holds in the department. I've been driving around last month of the summer in Mississippi and Louisiana. I was actually seeing quite a few of these things, where farmers have a little kind of wetlands, or just a filtration pond or something out here. They'll have riparian buffers, and a lot of our people are really adopted a lot of the practices already because they help. They help the farm.
They're getting conservation easement on the
Yeah.
CRP program.
Money.
Yeah.
Right. And so a lot of these things are going to be those sort of outer edge, right? They're going to be small, targeted, you guys need to kind of. And the city side, the lead group, actually has very much looking at practices and how to make green architecture and new building and that sort of stuff. But they have an actual program about green infrastructure in your cities as well. So it's not just the farmer community, but also cities can, quite a few cities started looking at case studies of how they can sort of better green their city, need a green infrastructure. To better manage the city. So one of the case studies that we have here, get back to that. The people, how are we actually benefiting people, right? Whether it's social equity, looking at health and wellness, resilience of the city and of the people. A lot of these things, these green infrastructure efforts, don't just make engineering sense, right? They make people sense. Here's an example of something that went kind of bad, but it's maybe going back. So this is the Klamath River. So here's Oregon, California. Klamath River right here. Big salmon breeding ground right here. This is the heart of the industry percent, right? All this good. So there's this Klamath River. So way back in the early 1800s, there was thousands of beavers in this area. Beavers make beaver dams all over this place. They fundamentally altered the ecosystem. Right? And the beaver dams, think about it from, here to salmon. You gotta swim upstream. You've got to go a long ways upstream. Having nice little beaver dams that you can jump over and then rest behind makes a lot of good sense. And so the salmon actually evolves in conjunction with the beavers in this landscape. So join the outgroup, right? That's one of the reasons why this area is so productive for salmon now, because historically there was a lot of beavers there, right? The colorful history of the mountain men of the West. It's an interesting read. The fountain men came through and killed all the beavers. Like thousands of beavers trapped in the early, so there was no more, right? Not long after that, you've got the gold rush. So then all of a sudden you've got gold miners coming in and digging up all the banks and digging up all the riverbeds. So you're spoiling everything. So now you fundamentally alter the ecological side of the watershed. You fundamentally altered all the time of transport hydrodynamics, right? Because you just changed all, just dug up all the river sediment to the gold, right? So this thing is absolutely nothing. So there are people who are trying to look at, well, how can we go back and at least restore some of this and go back to making this a good place for the salmon to flourish. One of the ways they're looking at doing this is artificial beavers. Artificial beavers. So this is a science journal article looking at who builds artificial beaver dams and encourage the beavers to come in. But in the meantime, we're now starting to provide habitat for all the salmon that we want. There's a lot of pros and cons for beaver dams. A lot of people are very, you're either pro beaver or anti beaver. There's not really an happy.
Just a guy who's destroying the beaver dams. That's all he does.
But there are actually studies of like, what is the value of a beaver dam in terms of hectares of land that it covers in water, right? So diminishing flood intensity, so let's put it by Yale. Diminished flood intensity, $144 a hectare a year. Filtering water, 108 hectares per year, $1 a hectare. Capturing greenhouse gas, $70. So you put all these together, you're looking at about roughly $684 per hectare. Multiply that by 1.8 million hectares of land covered by beaver dams, and you start to get big money coming out of this thing pretty quick. So the beavers actually make a lot of good sense. Now, Noah has a stream running through his backyard, and the beavers come up and build a beaver dam in his backyard. I'm guessing Noah would not be in the I'm happy to see the beaver here in his backyard, right? Because it's going to impact his house, people flood out his house, and probably go chew up all of his trees that he has on it. So there's the downside of beaver. So the timber industry, specifically here, or not here, but specifically Mississippi don't like beavers. Because they have a lot of timber.
Timber companies don't like.
Timber companies don't like beavers. So, there's a lot of damage to the timber industry. It's actually $90, $80, so probably more than that now. They're going to forage a good ways around where they are. So if you've got, corn or soybeans or whatever, they're going to go munch your fields, right? So, not so helpful there. Beavers, they're going to pick the easy spots to build their dams, right? So if you've got a culvert or something, they're going to be like, score right here. So that's so helpful, right? And then they'll build burrows. So they have burrows in water or in banks. It depends on how steep this water is and how fast the water is. But they'll build burrows in the side of the lakes here where it's like a road, right? At which point you now be further money your roads. So bad thing. So there are downsides to beavers. Not like beavers are the magical panacea of so there's a lot of programs to help control and manage beavers or kill beavers. There are groups that are looking at these beaver dam analogs. So how do we create the effects of the beaver dam? We can put a beaver dam where we want. Maybe we'll throw it, maybe we won't. But we at least have kind of the ecological impacts, the hydrological impacts of beaver dams. And you'll see these are really successful in sort of wild areas, right, where flooding, you want flooding, and you want the water to be sort of backed up and spread around and start to develop from simple ecosystems to complex ecosystems. So they have a different way of doing this. Usually you end up getting some locally harvested pepper poles, and you get some kind of vibrates them down, and we have to build this line of poles across the river. Start chopping down some willow, whatever, weave them in there, sort of make a line across your river. But it ends up looking kind of like this. Then the water is slowing down. There was a engineering with nature conference out in Yuma, and there's a lady that came and presented. She was like landowner of an area in Arizona. She like embraced this concept. She went hog wild. Like, she built like 300 pseudo beaver dams, but like out of boulders. Like she like got a little, excavator, moved like boulders into the stream. But there is, she's captured all the sediments. It was like mountains, terrain. So she's going to capture all the sediment that comes off behind all these boulders. And she's seen an impact on how water that pools there is like able to sort of create microhabitats. So
what they're doing there is got an advantage that the willows will grow. So that's a living structure, not just a dam. It'll come alive. You went back in 10 years, it would have 30-foot high willows across. You don't even the dam. You wouldn't even see the dam anymore. Unless the beavers came and ate them.
So this is another, technology that can be applied to engineering with nature, right? We're going to manage ecology, we're going to manage water, we're going to manage geomorphology, and sort of put it together. Sort of put different ideas together last night and sort of think through where on the spectrum would different kinds of these practices work well together. So beaver dam analog, you're probably like more higher order thing, right? If you're down here, you're gonna have a pretty big beaver dam, right? So probably somewhere up here, right? And digital practices, you're gonna be transitioning from your open space, right, to your first order training. Right? Your constructed wetlands. There's quite a bit of like Google bioretention thing, constructed wetlands. Pretty much every state was like, oh, this is so awesome. We're gonna have like throw a giant manual at you, training courses on how you kill stuff. There's a lot of good stuff. So, but you're gonna target sort of higher order things here, right? Urban sites for water disconnects, right? Bioretention stuff, cropping and tillage B&Bs. It's not until you get to more like your bigger infiltration basins or your large scale river restoration, that you're kind of more down lower in the watershed with your projects. The last few are really just some guidance, some links basically from the EPA. They actually had, I was surprised they had a really number of instructions on how do you actually build these things. Principles to think through that make it successful or not. So here's one for how do you make constructed wetlands. Lots of guidance there. And they even sort of connect to regulatory issues and waters of the United States, and sort of how does that all tie together. Stormwater, bioretention, rain gardens. What makes this work? How effective are different sizes? Infiltration basins, if you can design one, what needs to go where so that it actually infiltrates and work out instead of just kind of the stagnant amount of water that breathes. So hopefully that all sort of pulls it together.
Yeah, jet.
So again, engineering with nature is really, go back to what I said, the intentional alignment of natural and engineering processes. So we are sort of in a rich playground of processes that happen at different scales, at different times and places, where we can actually make a big difference. If we adopt this mindset of how do we manage processes and align control and engineering.